In the previous video, we discussed the design of Spur gear teeth using the Lewis beam equation. In this video, I shall discuss design of teeth against fatigue failure, followed by the AGMA approach for the design of the gear teeth. The slide shows the contents of this video. The velocity factor CV in the modified Lewis beam equation, which is given here for ready reference, basically has been introduced to take account of the dynamic nature of the tooth load. It was assumed that the velocity factor depends on the quality of the gear and the pitch line velocity only. However, Buckingham developed an expression for the dynamic load in terms of the pitch line velocity, the tangential tooth load, combined gear tooth spacing and profiles errors, beam width and elastic constants, that is Young's modulus of elasticity of pinion and gear materials. As discussed earlier, the dynamic loading may lead to fatigue failure of the teeth, which are the fatigue fracture of the tooth and the wear and surface fatigue of tooth. In the present video, design of the gear teeth against these modes of failure is being discussed. The Buckingham's dynamic load equation is given here, where Ft is dynamic load, Ft is tangential tooth load, V is pitch line velocity, B is beam width, and C is known as dynamic or load stress factor, which is function of the probable error in action between gears. K1 is a constant. Ep and Eg are Young's modulus of elasticity for pinion and gear materials. We know that as the velocity increases, the dynamic load increases. So to keep the dynamic load in control, with the increase in velocity, lower permissible error must be there, and this is exactly being reflected in table 1. The probable error in gear action is given in table 2 as function of the module and the quality of the gear. The quality of gears have been classified as precision gears, carefully cut gears, and commercial gears. We can see that the probable error increases as the module increases and as the quality of the gear decreases. The value of constant K1 as function of pressure angle system is given here. The endurance strength of the tooth, that is the strength of the tooth against fatigue fracture, is given as Fen is equal to sigma En, that is endurance strength of the gear tooth material, the beam width pi ym, and stress concentration factor Kf. Sigma En, that is the endurance strength, is related to ultimate strength for steel by the relation sigma En is equal to 0.5 sigma u. For cast iron, it is 80 to 120 MPa. For steels, sigma En is related to the Brenner hardness by the relation given here, and it can be easily interpreted that the endurance strength can be increased by increasing the hardness. The stress concentration factor, which was discussed earlier, is given as 1.6 for 14.5 degree system and 1.5 for 20 degree system. The endurance strength of the tooth must be greater than the dynamic load by a margin of safety. We discussed three modes of failure of gear teeth, and it was also mentioned that uprooting of the tooth or fatigue fracture of the tooth is the worst kind of the failure and must be avoided. That's why a margin of safety is desired. It is 1.25 for steady load, that is, the fatigue strength is 25% higher than the dynamic load, and it is 1.35 for medium shock condition and 1.5 for heavy shock condition. If the endurance strength Fen is less than the dynamic load Fd, proceed in the following sequence till the above condition is achieved. In case of steel gears, increase pinion and gear hardness, which increases the endurance strength sigma En. We have seen that sigma En is related to the hardness of the material. However, BSN is kept less than 400 for plain carbon steels and less than 450 for alloy steels. To some extent, the beam width may be increased up to 12.5 module if we have selected a lower value, say 10 module earlier. Use better quality gears. This reduces the error E and hence the dynamic load is reduced. This increases the cost of the gearing. Use material of greater strength. The last measure is to increase the module. Now we discuss the surface fatigue of the tooth. The limiting load for wear, which is actually the wear strength of the tooth, Fw, must be greater than the dynamic load. The relation of Fw is given here. In this relation, Q is ratio factor and its relation is given here. K is known as material combination factor, which is function of the surface endurance strength of the material, the pressure angle and the Young's modulus of elasticity for pinion and gear materials. For steel, the surface endurance strength can be calculated from the given relation, and for cast iron, the values are given on the right. For 20-degree pressure angle, the value is 1.8 for cast iron pinion and cast iron gear. It is 1.6 for cast iron pinion and phosphor bronze gear. The value of K is 1.3 and 1.2 respectively for 14.5 degree system. Normally, the cast iron gears do not fail in wear. The wear load capacity of steel gears can be increased by increasing its hardness. Pinion is provided greater hardness because it is subjected to greater number of loading cycles and wear. I take up an illustrative example to explain design against fatigue. The gearing data obtained from the previous design based on the Lewis-Peave equation for the type 1 problem are reproduced here. 20-degree full depth teeth, module 4 mm, beam width 44 mm, number of teeth on pinion gear. The diameters are mentioned here. The form factor was 0.108 for pinion. Material was C40 heat treated steel. The pitch line velocity was calculated as 3.64 meter per second and the tangential tooth load as 6.74 Newton. The dynamic load from Buckingham's equation can be calculated by selecting the probable error. The permissible error for pitch line velocity 3.64 meter per second is 0.075 maximum from table 1. We select commercial gears with probable error 0.05 mm for module is equal to 4 mm from table 2, which is less than the permissible error. The Young's modulus of elasticity for steel is mentioned. The factor K1 is equal to 9.0 for 20-degree pressure angle. Knowing the probable error in gearing action and factors K1, EP and EG, we can calculate the load stress factor C, which comes out to be 575. Now, knowing all values in the Buckingham equation, we can calculate the dynamic tooth load, which comes out to be 15547 Newton. For steel C40 heat treated, the surface BHN has been mentioned as 300. The core BHN will be somewhat lower, say it is 200. Then the endurance strength of the material is 1.75 times of BHN, that is 350 MPa. For stress concentration factor of 1.5, for 20-degree pressure angle. Now we get the endurance strength of the tooth as 13933 Newton. This doesn't meet the requirement of Fen divided by Ft greater than equal to 1.35 for medium shock condition, which has been assumed for electric motor compressor combination. We can calculate the required endurance strength of the material by equating the endurance strength of the tooth to 1.35 times of dynamic load Ft, and this gives endurance strength required for the material as 527 MPa. As the tooth hardness must be increased to Bhn is equal to 527 divided by 1.75, that is equal to 300. The pinion hardness must be kept greater than that of the gear by about 50 Bhn. Hence use 325 Bhn for pinion and 275 Bhn for the gear. Now we consider the surface fatigue. The limiting load for wear, that is wear load capacity of the gear tooth, is given by Fw is equal to dpbqk, where Q is ratio factor given by 2Zg divided by Zp plus Zg, and from given data it comes out to be 1.556. Equate the wear load capacity to the dynamic load and solve for the required value of the material combination factor K. This gives K is equal to 2.84. From the relation of the material combination factor in terms of surface endurance strength of the material, the pressure angle, the Young's modulus, the required surface endurance strength is sigma ES is equal to 1097 MPa. The surface endurance strength relation sigma ES is equal to 2.78 Bhn minus 70 MPa gives the required surface hardness, which comes out to be 420 Bhn. Refer step 2, that is the design against the fatigue fracture. The value of the form factor Y of the pinion is always smaller than that of the gear. Hence, when material used for the pinion and gear is the same, the pinion is always weaker and hence it is designed. The endurance strength equation may be written as Fen is equal to product sigma En into Y in brackets B pi m divided by the stress concentration factor Kf. The pinion and gear can be made of equal strength if the material of the pinion has greater endurance strength to give equal value of the product sigma En for the pinion and the gear. Unlike equation of endurance strength Fen, the equation of the limiting load for wear Fw is a combination equation. That is, it is not different for the pinion and gear. Now I discuss the American Gear Manufacturing Association AGMA approach for the gear design. The Lewis beam equation has been the basis for the conventional design. Its use implies that the teeth do not share the load and that the greatest force is exerted at the tip of the tooth. In fact, the gears are cut with sufficient accuracy and the tip load condition doesn't occur because another pair of teeth will be in contact. You must have read in the theory of machines that the contact ratio is always maintained greater than unity. Examination of run-in teeth has shown that the heaviest loads occur near the middle of the tooth. Therefore, the maximum stress condition probably occurs when a single pair of teeth is carrying the full load at a point where another pair of teeth is just on the verge of coming into contact. The American Gear Manufacturers Association developed an equation for the bending equation with modified form factor to overcome both of the above objections and also to include the effect of stress concentration, which is a function of the fillet radius at the junction of the involute curve and base of the gear. The AGMA equation is written here and the Lewis equation has been rewritten with pi y being replaced by capital Y. The comparison of the two equations shows that the factor capital Y in the Lewis equation has been replaced by a factor J in the AGMA equation. The values of the Lewis form factor Y and the factor J, which is known as geometry factor, are given in tables 1 and 2 respectively. See the tables critically. A comparison of the tabulated values of factors y and j shows the following. Typically for Zp is equal to 18 to 21 and Zg divided by Zp less than equal to 4, the value of factor j lies between 0.324 and 0.372, while for Z is equal to 18 to 85, the value of factor y ranges from 0.293 to 0.423. Thus, at the lower end of the range of the number of teeth, the Lewis form factor y is smaller by about 10%, while at the higher end of the range, the factor y is larger by 15%. Normally, in a design problem, module is to be estimated since the diameter and hence the velocity and tooth load Ft and the beam width B are expressed in terms of module M. The calculated module from the Lewis beam equation is proportional to y power minus 1 by 3. Please refer the solution of type 1 problem using the Lewis beam equation. Thus, a difference of 10 to 15% in the values of factors y and j will affect the estimate of the module by 1.1 power 1 by 3 to 1.15 power 1 by 3, that is by plus minus 3 to 5% only, which is not significant. The design of Spur gear teeth has been discussed considering the three possible modes of the tooth failure. The AGMA approach, which is a modification of the Lewis approach, has also been discussed. A detailed presentation and discussion of the design of the gear shafts and gear blanks are presented in the next video. It has been mentioned that for a given problem of spur gearing, many solutions are possible and these solutions must be considered to identify the optimum solution for the given design criterion. Hence, the computer-aided design is adopted, which is also discussed in the next video. However, the selection or design of the bearings to support the shafts will be treated separately. More details can be seen in the references given here. I hope you have liked the video. Please feel free to send your questions at my email address given on the first page. Please wait for the next video. Thanks.